record. So we should be good here. Okay, so last class, we left off talking about sample size calculations within the context of SRS. We derived a formula to compute the sample size for an SRS based off of how much of a bound we would expect on the bound that we would like to have on the confidence interval. So this is a pretty standard procedure for finding sample size within the context of well, any estimation process where we want to use a confidence interval. You might recall from your earlier studies, we basically had the exact same practice in Stat 151, Stat 252. The only difference was that we didn't have the finite population correction within the standard error formula. So that led to a different result. But we can show if the sample size is large enough that we converge to that result anyways. And the sample size being large enough is really dependent on how many, how large or small we want the bound to be, and what we know about the previous variation within the population. So those two factors combined would influence the what would qualify as a large population size. But for example, here, when we considered bounding, when we wanted to create a confidence interval for the women in the PIMA study, we wanted the bound on the interval to be 3 units. We had a previous variation of 370.6284. And in that particular case, n being large enough was actually around the factor of 1 million. So n somewhere in the neighborhood of 1 million, or a size of 1 million for the population, would be large enough that we could ignore it. But before that, we actually noticed quite a bit of deviation between the values if we have kept the finite population value in, or if we ignored it, which is what we have illustrated on the slide here. Okay. Okay, so there's a second example here, which I've given myself lots of room to write down. Do I have any spare room anywhere? Okay, what I'll do, so question B is basically the same thing. I'll just give a few little indicators of how we would approach this. So in this case, I guess I can just write it up here. Okay, so the process for B would be the same. So we have the same formula. So we're going to use n is equal to b squared over z alpha over 2 squared sigma squared plus 1 over n. The difference here is that our estimate of the standard deviation is going to be built using the range that is given to us in the population. So here we can say that sigma hat is approximately 846 over 6. So one general rule of thumb for estimating the deviation in a population when you only have the range available to you is to divide the standard deviation by 4 or by 6. And this can give kind of a crude approximation of the standard deviation. So in this case, we could use, for example, 846 over 6 to approximate the standard deviation. And if we do that, we should be able to show in the end that little n works out to be somewhere in the area of 706.6816, which means that we would need a sample size of approximately 707. But I'll leave this just kind of as a little verification problem because of the space limitation, but you can imagine how this would work out. You're basically just plugging into our sample size formula from above. All right. Okay, any questions from the live audience? Any questions from the virtual audience? The virtual audience is small today as well. All right. Okay, so as a reminder, the material for the first quiz is going to stop here. So the sample size calculations is where we'll cut off for quiz 1. So the next set of material will be for assignment 2, quiz 2 onward. So the question was, will anything from assignment 2 be on the quiz? And the answer is no. Yeah. Okay, so the next thing that we're going to talk about within the context of a simple random sample is estimating a population proportion. And as you might imagine, this is going to work in an almost analogous way to how we estimated the population mean. The big difference here is that the variable or the feature that we are measuring is no longer continuous. It's now qualitative. And in fact, it's actually binary. So the thing that we're measuring or the value that we're interested in is a binary variable that indicates whether or not the observation has whatever the feature is that we are curious about. So proportion estimation is used quite often in practice. For example, on assignment 1, the very first question was kind of like a proportion question, except that you had multiple outcomes within the survey. But if you think about it in the most basic context, the first question on the assignment was basically saying, did you or did you not visit friends or family over the weekend versus, well, actually, it's did you visit friends or family over the weekend versus did you not visit friends and family over the holidays, sorry. So you can think of that as a proportion where 1 could be for the people that visited and 0 could be for the people that did not. So then we can count how many people actually visited friends or family, and then we can build a proportion based off of that. So other examples of where we might see a proportion being used, in elections, this would be common. Again, a little bit different there if you consider the Canadian system because we have multiple parties. But if you think about the 2 major parties in the US, it's really kind of a binary choice. You go red or you go blue. So you could assign a 1 to the Republican Party and a 0 to the Democrat Party, for example. What proportion of people smoke marijuana regularly could be another question that you might be interested in. In this case, you'd be defining bounds based off of what you think is regular, but the idea is the same. The value that we're, in the end, the value that we are interested in is either a 1 if the observation has the characteristic that we want to discuss and 0 otherwise. So the estimate of the population proportion, which we designate as pi. Okay, so pi here represents the true proportion of whatever feature you're interested in the actual population. The estimator of pi is simply the sum of all of the 1s attached to the variable. So the sum of the zi divided by little n. So it's essentially just a count of all people or all observations that adhere to the characteristic. Okay, divided by little n, which is the sample size for the entire experiment. And we can show fairly easily that pi tilde is an unbiased estimator for pi. Okay, we can also show that the variance of zi, which is our indicator, is capital N over n minus 1 times pi, or times pi times 1 minus pi. And I believe that this is the second question on assignment. This was the second question on assignment 1, which is now the first question on assignment 2, which is to prove that this is the case. And then we can show from that the variance for pi tilde is given below, which means that our estimate of the variance of pi tilde, or the estimate of the variance of the estimator for pi, is just going to be similar to what it was in the SRS case, the finite population correction. Okay, and then multiplied by this quantity, which is sort of like the standard error of pi tilde when n is infinite. But the form is pretty much exactly the same, which is the big takeaway here. So our estimation of a proportion is going to act very similar to our estimation of a population mean. Do you guys want me to close the door? Yep. Yeah, so the question was, are we typically going to be referring to SRS without replacement? These formula are for SRS without replacement. And we could derive the same estimators in the SRS with replacement setting, but the examples that we'll show are without replacement. Okay. Miriam, question 2 from assignment 1 will not be there, right, on the quiz? Yeah, that's correct. Yes. So again, the proportion stuff is not going to be on quiz 1. Okay, so let's look at a little application of our formula here. So we have from an SRS of 3,078 counties, we found that 153 of the 300 sampled counties had fewer than 200 acres in their farms. Estimate and give an approximate 95% CI for the true proportion of counties with fewer than 200 acres in farms. Okay, so let's just take a look at what the indicator is here so we have an idea. So we have ZI 1, 0. So it's 1 if a county have fewer than 200,000 acres in farms and 0 otherwise. Right. Okay. So then what the question is telling us is our population size is 3,078. Our sample size is 300. And then what it's saying is the sum from I in one, or the sum for all I in the sample of the ZI is equal to 153. So going back to the point I was trying to make before, these proportion style questions are meant to get counts of an observation that adheres to a certain feature. And we can set up proportions in many different ways. So for example, here we're counting the counties that have fewer than 200,000 acres in their farms. But we could do the same thing with elections or questions related to the current social environment, as we have seen in previous illustrations. All right. So from this, we can show pi hat is equal to 1 over n times the sum I and s of zi, which is going to be 1 over 300 multiplied by 153, which is 0.51. All right, now we want to bound our estimate. So the variance of pi hat is equal to 1 minus little n over capital N times sigma over little n, I believe. Make sure I have that correct. Yeah. And no, this isn't correct. So it's this over n, and then this thing becomes 1 minus little n over capital N, pi I, 1 minus pi I divided by n minus 1. Okay, all right. So then this thing is going to be 1 minus 300 over 3078 multiplied by 0.51 times 0.49 divided by 299. And then this thing, I don't have the exact number, but it's going to work out to be 0.275 squared, which is fine because we just want to bound it anyways. Okay. So then we can say the 95% CI is given by 0.51 plus or minus 1.96 multiplied by 0.0275. And that should give us 0.4561 to 0.5639. All right, so then we can say we are 95% confident that the proportion of farms with less than 200,000 acres, or sorry, the proportion of counties with less than 200,000 acres in farms is between 0.4561 and 0.5639. Oh, yes. Yeah, sorry, that's a good point. We would want to do that. Should be fine in this case, but let's make sure. So the question was, should we do the same check for the FPC? And we should have checked that. But I think it'll be fine because that's going to be like just under 0.1. So yeah, 0.9. All right, so we can also make the note here. 1 minus 300 over 3078 is equal to, that would be approximately 0.097. We'll see. Sorry. There we go. Yeah. So the FPC check, we're right around 0.0. We're right around 0.9, not greater than 0.95. So we would keep it in the calculation anyways. Thanks for that. Good question. Any other questions? Virtual world? Okay, so that brings us to the conclusion of the simple random sample part. of the lecture set. As I mentioned before, the simple random sample fundamentals will make up the other sampling schemes that we see later in the course. So, well, we're about to look at what's called systematic sampling, which is really very closely related to SRS. But we're also going to talk about stratified sampling in the next lecture set, cluster sampling, and some other procedures later on. And they're all at the base of them related to SRS. Well, they're all built off of SRS, I should say. Okay, so just a few notes of when we might want to use a simple random sample. So for example, if there's limited information about the elements in the frame, we could be interested in using an SRS. When trying to appease a researcher without violating assumptions, and this one kind of just dates back to the inferential assumptions that we have for hypothesis testing and confidence intervals. So we always teach that you assume simple random samples and you assume normality. So if we're designing a research study, we'll say we're going to use SRS to make sure we can check off all of the assumptions if you're particularly strict. Or when trying to establish complex relationships for large populations. So as you might imagine, using SRS in very big populations could be useful. But depending on, as we will see later, depending on the structure of the population and what it is that we're interested in collecting, the other sampling schemes could be more helpful in actually retaining information. But we will also show later that through the coefficient of variation, we can compare the estimate from our simple random sample to the estimate from, say, our stratified approach, and then actually make an argument based off of those values as to which one is performing better for the given situation. Okay, so systematic sampling. Systematic sampling is very closely related to simple random sampling. In fact, as we will see, it actually uses the same estimates that SRS uses. The difference between systematic sampling and simple random sampling are that systematic sampling doesn't actually require a sample frame. So it can be very helpful in situations where finding a frame would be impossible, let's say. And we'll look at a few illustrations of when that could occur momentarily. Okay, so what is systematic sampling? Systematic sampling is essentially an approach where you choose every kth element to enter into your sample. So you can imagine in the simplest situation, imagine you have a line of, let's say 100 people or 1,000 people or 10,000 people or something like this, and you just choose every 10th person or every 20th person. So you walk through the line and you just go, you're in, count to 20, you're in, count to 20, you're in. That's essentially what systematic sampling is. The way that it would work in practice is you would randomly select one element from the first K elements in the sample, where K defines like the jump point, if you will, so the gap. So you can see here, if we have 100 people, for example, and our K is equal to 10. Okay, so that's for this part here. We randomly selected one number from 1 in 10, which was 7 in this case. So this is randomly selected from 1 in 10, or 1 to 10. Okay. So we randomly pick 7 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then from 7, we just counted by tens until we filled our sample, or until, in this case, we got to the point where there were no observations left. So we start at 7, add 10, and then we conclude at 97 because we only have 100 people available to us, so we can't, obviously there is no unit 107, for example. Okay, so compared to SRS, as I said before, they're actually very similar, and we'll show that they use the same estimates, though we can make an argument as there are situations where we will expect systematic sampling and simple random sampling to basically give the exact same solution. And then there are situations where we will expect SRS to have increased variation compared to systematic sampling. And we'll talk about those in a little bit. But just going back to the original point about the lack of requirement for the sampling frame. So a few of the advantages of systematic sampling are, again, in general, it's easier to perform. You could say this because you don't have to have the frame and you don't have to select from the frame. Though, I mean, you might argue that that isn't overly taxing anyways. But let's say, for example, you want to sample, like shoppers from a particular store. So you're standing in front of like a Shoppers Drug Mart and you want to sample people that went in and came out with something that they purchased. There is no frame for this problem because you don't know on the given day or wherever or through whatever your sampling period is, who's actually going to be going in and out of the store and buying something. So you can basically pick a K, select your first unit, and then stand there and then go 1, 2, 7, take the 7th person, ask them their question, and then move on with the day. Well, at least you could do this. Maybe you can't anymore, but this is the idea. And going back to the idea of not having a frame, this is where systematic sampling would be useful because you don't have to randomly select from a frame that doesn't exist. Instead, you can just take every kth observation into the sample. Systematic sampling also gives you sort of like a uniform spread over the population. I mean, you might argue that this could be more representative, though, again, we're going to look at situations where this uniform spread could also lead to problems compared to SRS. But the idea here is essentially you're splitting every time you sample, it's getting split into equal units. So maybe that uniform spread of the observations is going to give you something that's a little bit more representative than in the SRS case, or maybe you don't risk collecting a chunk of people that are very similar just through like a bad random sample or something like that. Okay, so a few basic examples. So let's consider quality control for a particular device or, cooking unit or any kind of product that's coming off an assembly line that someone might want to buy and put into their house. So systematic sampling would be a natural way of collecting a sample in this case. So if you consider an assembly line, you have the units moving across the assembly line. You want to inspect them at a certain point of the process to check to see if they adhere to a certain characteristic. Then you can select every 5th unit, every 10th unit, every 15th unit, for example, to be a part of your sample. And then you can use that information while they move through the process to check the units and say that this would be representative of the entire population moving through the assembly line. So I also have here, consider the inspection of work done at fixed stations. The plan may call for sampling of the output at each station every 3 hours. So this could be another example of a systematic sample where you have to go into the station, evaluate this criteria, and you pick a certain time frame in which you're going to visit the system. So every 3 hours, every 4 hours, every 5 hours, things like this are all examples of systematic sampling that would occur naturally as we work through, that would occur naturally to validate products or to assess the reliability of a certain station or system. All right, so when we're constructing our systematic sample, the language that we use to define the systematic sample is 1 in K, right? So the K, again, represents essentially like the jump point, so the gap between the units in the sample. And it also tells us where we would sample from to pick the starting point, right? So going back to the previous illustration where we had K is equal to 10, we're going to pick a value between 1 and 10. That's our starting point, and then we're going to jump every 10 units from there. Okay, so the bound on K is the population size divided by the sample size. So K must be less than or equal to capital N over little n. So for example, if capital N is 20,000, little n is 200, K cannot exceed 100 since, well, as you can see, 20,000 divided by 200 is 100. It follows that one back or sort of downfall of the procedure is if we don't know capital N, then we can't reliably pick K to be within this bound. Okay. All right. So as I mentioned earlier, for systematic sampling, we use the same estimates that we would use for simple random sampling. Okay. So you can see in equation 2, we have our estimate for the mean, and we have our estimate for the variance of the estimator for the mean. And we could also write these in our random variable notation as well, but the point is just that we use the same estimators as what we use for SRS. Okay, the consideration that we actually have to make here, though, is that for systematic sampling, and we'll talk a little bit about this later, we can actually show that the true variance of the systematic sampling estimator of the mean is not the same as SRS. So the actual variance is given in equation 3. So for a systematic sampling system, the estimate of the mean, of the population mean, has a variance given by sigma squared over n multiplied by 1 plus n minus 1 times rho, where rho measures the correlation between pairs of elements within the sample. We can show in certain situations that rho is going to be 0. And if that is the case, then we can show that these estimates are approximately equal to one another with the compensation of the FPC, of course. But in other situations where rho is not close to 0, obviously the estimates of the variance are going to diverge from each other. We will talk about methods for calculating rho later on when we talk about repeated systematic sampling, as this will give us a strategy for estimating rho. But in the context of just systematic sampling, we typically utilize our SRS estimators because we would assume in that case that we are collecting a random sample of elements that are not related to one another. And in that situation, you could argue that rho, which measures essentially the correlation between the measurements in the sample, should be 0 if the values are all unrelated. Yeah, so if rho is 0, then n minus 1 is canceled out. Yeah. Any questions about that? The question on the floor was just, so if we have a random sample where the observations are uncorrelated, that implies rho is 0, and that is indeed the case. Do you think I get crazy feedback if I push this? I think I would. Scared. Just destroy yours. All right. And then as a note at the bottom, if we want to estimate the population total, so tau, we would have the same correction being applied to our variance and our mean estimators. Okay. So going back to the previous point, we have established that for systematic sampling, we use the SRS estimators most often. However, we know that the true estimator for the mean from a systematic sample is not actually equal to the variance of the estimator for the mean of an SRS. So how do we know when it is appropriate to use, say, these estimates from SRS in the systematic case? All right, as we established, when rho is close to 0, we're going to get basically the exact same variation. So the idea would be we would use these estimators when we have evidence that rho is close to 0. When rho is close to 1, what this would imply is that the elements within the sample have measurements that are very similar to each other. And in this case, we would say that the systematic sampling will act as will have a higher variance compared to SRS. Okay. So in this case, just want to make sure I get this right. We can write that SRS is going to act as a lower bound. I just want to make sure I get that. Okay, so in this case, we can say that SRS will act as a lower bound. And then when rho is negative, we would say that the systematic sampling estimate will yield a more precise estimate of the mean. So in this case, we would say SRS acts as a lower bound. Okay. So the implication here is, again, if rho is close to 0, the estimates of the variation are going to be very similar to each other. So we can kind of go either way with it. If rho is close to 1, the SRS estimator of the variance will be less than the variance, or would be less than the variation of the mean estimator from systematic sampling. So if we wanted to cheat, we could use SRS instead to get a more precise interval. And then when rho is negative, that's going to force the systematic sampling estimate to be decreased compared to SRS, which means that it would provide the more precise interval. All right, so we have these ideas established. We're building up an understanding of how the estimators for the variance of the means behave in different situations. So what would be actual examples that we can look out for in order to have an idea of how the systematic sampling estimate is going to behave compared to the SRS estimate? So what would the data potentially look like? What would the data look like, or how would the data be structured such that we could say we would expect one of these three situations to occur? So we're going to consider three different styles of populations: the random population, the ordered population, and the periodic population. So these three populations, each one gives an illustration of when we would expect SRS to be the lower bound, when we would expect the estimators to be equivalent in terms of their variance, and when we would expect the SRS to act as an upper bound. So as you can imagine, the random population would be one where all observations appear to be unassociated with each other and not related. And this would be the situation where we would expect the two sampling approaches to have variation estimators that give similar results. The ordered population is the population where the elements are going to have a trend associated with them. So the values are either going to be increasing or decreasing. Okay? And in this case, we'll explain in a second why we would expect, this is a situation where the value of rho would be negative. And as a result, we would expect SRS to act as an upper bound. Okay, so for clarity here, we have rho is approximately 0. Here we have rho is negative. And here we have rho is positive. Oh yeah. And then the last situation is the periodic population, where we would expect the values, well, the values are going to display sort of like a cyclic nature. I'll show an example. I'll sketch an example momentarily, but you can think of like a sine curve or a cosine curve. And in that situation, you would expect the values to be positive depending on when you actually collect the information. So depending on what the value of k is, you could expect or see positive correlation here. All right, so to illustrate these three ideas, I'll draw some sketches here. Okay, so we'll start with our random population. And let's do it like this. Okay, so the random population is essentially just the cloud or the ideal turnout from like a residual analysis kind of idea. So we have the yi on our y-axis, we have the sample value number or the observation number, if you will. Let's write observation number here. And actually, let's do, just to make it a little bit more clear, let's take another set of plots. Okay, yeah, this will be good. Okay, so let's imagine that the first plot is the actual population, and then the second plot is the sample. So capital N is just to represent the population, and then little n is to represent the sample. Okay. So the random population is basically going to look like a cloud. So I'll just use little dots to represent the values here. So if you just randomly assort the dots, these are the observed value all over the place. And then to be completely like, if you want to be really strict about it, there shouldn't be, actually we'll just say that the axis is super tight. So if the points look like they're stacked, they shouldn't actually be stacked at any point because they're individual observations. But this is the idea. Okay, so now suppose that you select a 1 in k systematic sample from this. So you let k be 5, and so you take every 5th observation. When you pop it out, you know, you should have something that looks like this. Okay, let's say, for example, maybe I'll just fill it in a little more like that. Right. So this still looks random. There's no apparent order here. There's no trend. It's just a random assortment of points. So this would be the situation where, as you can imagine, you would expect rho to be close to 0. Okay, so here's the idea when we talk about the ordered population. I'm going to use 2 different colors here to represent downward and upward trend because technically order can go in either direction. So let's let red, or actually I'll use colors I haven't used before. So let blue be upward, and then let green be downward. All right. So the downward trend would essentially look something like this. Right. Okay, so the idea here is if we were to apply a systematic sample to this arrangement of observations, what's going to happen is the values are going to start to naturally spread out from each other. So if we were to then consider the sample value, you'll start here, say, and then you'll be here, and then you'll be here, then you'll be here, and then you'll be here. Okay, so there's a trend in the data. I mean, you can imagine that the sample is larger so you can see the trend a little bit more. But the idea is there's a trend in the data that's going, regardless of the direction, it's going downward in this example. The values are spreading out from each other. And that's what the negative correlation represents. So this would be a situation where rho is negative. Okay. And then obviously the magnitude of the correlation is going to depend on how far separated these points actually are. But the idea of the negative correlation refers to a trend in the data. So in this case, a decrease, but a spreading out of the values. So the values are moving further away from each other. So they're related but negatively correlated. And then it's the same idea if we were to go in the upward direction. Okay. So let's say like this. So bad at this. I always stack the points. Hopefully you get the idea. Okay, so you have a trend line that's going up now. You collect a sample from this. It's going to be the same kind of idea, like that. But again, it's the same result. So we still have a row that is negative. So the row is not referring to the direction of the trend. So the trend can be positive or the trend can be negative. What the row represents in the case of systematic sampling is the spreading out of the values from one another across the trend. Okay. All right. And then the last one. So the periodic population can lead to a positive correlation for the following reason, but you can get around this depending on the value of K you pick. So let's suppose that we have something that looks like this. Okay, so the idea here, now you'd have to sort of imagine, if you will, that this trend continues for a while. So imagine you have a longer time period and you're observing a cyclical trend across the time period. So we have lots of valleys and lots of hills. If you always collect at the same time period, one of the risks that you can observe, say for example, is you sample here and you sample here. Okay, so always sample at peak. Okay, so if you were to always sample at the peak, let's say, well, so I have only two observations based off the illustration, but you can imagine that you would have more and more peaks. This is an example of the positive correlation. The values are related to each other as you're always taking from the peak of each curve. Okay, so on Friday, I'll pick up with the periodic idea. I'll go over these concepts again, and then we'll move on to look at some examples of the SRS, of the systematic estimators, and then we'll talk about repeated systematic sampling. So Friday, I'll lecture from the home office, and Monday we have the quiz. Again, please let me know if you need accommodation of any sort, if you have any questions about this, the room or things like this. And otherwise, have a good couple of days, and I'll talk to you guys on Monday.